Well, guys, I think I'm just a little bit too excited to get started, so I think I'm going to jump back in right now and start talking about the Math 250B course. Um, Let me start off by just saying that we're definitely going to get our money's worth here. When I learned differential equations and linear algebra, I learned them as two separate classes. I took a course on differential equations by itself, and I was puzzled for half the semester why we were talking about these other concepts that didn't look like differential equations at all. So that didn't make sense to me. And then I took a separate course on linear algebra, and I spent most of that semester saying to myself, what is this stuff good for? I didn't see the connection, and both classes, I think, were weaker than they could have been. And only after I realized that putting these two subjects together makes sense have I been able to appreciate both of them more. I mentioned a few minutes ago, guys, that this was the subject. This was the class that got me excited about math. It made me want to be a math professor, and it made me want to learn more about advanced mathematics. I'm hoping that you guys will have a similar feeling and that you'll also very much enjoy seeing the synthesis of these two topics. So as a quick overview of the way we're going to do this, we're going to spend the first couple of weeks just doing some differential equations, okay? It'll feel a little bit like calculus. There's going to be some integrals to calculate, things of that nature. But then pretty quickly, we're going to kind of run up against a wall. And we're going to say, look, if we want to be able to solve even more differential equations, we need more tools. And linear algebra is the tool that we're going to spend a number of weeks learning so that in the last month of the semester, we can go back to the differential equations again with a much, much better understanding of everything, really. Much more maturity, much more in the way of a toolbox, and we're going to be able to do much more with differential equations. So this is the strategy. We start with differential equations, then we'll move to linear algebra fairly quickly, and then the last month of the semester, we'll be going back to differential equations, but we're going to be weaving these subjects together as much as we possibly can along the way. Okay? So that's kind of a big picture of what Math 250B is all about. I'm going to start with just kind of a quick little introduction on the differential equations side tonight, and kind of get started in the first couple of sections of the book as well. I'm going to be using this whiteboard here. I'm hoping everybody can see and read that fairly easily. Hopefully it'll come out clearly. You guys have to let me know if you're not getting something that I'm writing down. I'm going to try to do this like a traditional, lecture with a whiteboard. That's going to be kind of my game plan here. So hopefully it's going to work out okay. All right. So let's get started. I'm going to first just remind you what a differential equation is. Just a definition, okay? So I always like to put my definitions here and get them written down. Differential equation will usually just be abbreviated DE. So a differential equation is an equation. It is an equation involving a differential equation is an equation involving one or more derivatives of an unknown function. It's an equation involving one or more derivatives of an unknown function. And I'm sure that you saw these in calculus, right? And our goal, of course, is going to be to solve for that unknown function, right? Let me write down a couple of examples. So here's an example number 1. So EX just stands for example. So for my first example, suppose that we had dy dt equals 100 minus y squared. Okay? There's a derivative and there's an unknown function. Can somebody tell me in the notation that I've used here, what is the unknown function in this case? Like, what's the notation for the, I'm not asking you to solve the equation for the unknown function, but what is the notation? Which letters or which letter or letters would you give me for the unknown function? Yeah, so the unknown function is actually y, right? And y is the unknown function, and it's a function of t. So I'll write it as y of t. So what we would hope to do would be to solve this differential equation to come up with a formula for y of t. That would be the idea. Let me give you one more example. Suppose that we had, I don't know, a double prime minus 4x squared a equals 3a prime. Okay, so this is another example. And can somebody tell me for this example, what is the unknown function in this case?
X of a.
Is it x of a? Is x the function and a is the variable, or is a the function and x is the variable?
The second derivative of a.
Yeah, so you're taking derivatives of a, right? And when we're taking a derivative of something, we're taking a derivative of a function. So the function is actually a, right? A is the function, and a is a function of x, right, in this case. So the function is a, and the variable is x here, okay? So in both of these cases, we have a differential equation, and we know what the unknown function is that we would be trying to find. It's just not always that easy to find it. Guys, I have a news flash for you. Most differential equations are not solvable. And even after 15 weeks of the semester here, we will not know how to solve that many equations. We're going to learn how to solve some of the more important ones, the ones that come up a lot in engineering and in physics. We'll learn how to solve all of those, but many specialists in differential equations have to content themselves with maybe drawing a picture of the solution, or maybe just doing a numerical approximation to what the values of the solution would look like, or maybe just a description, a qualitative description of the solution. It is sometimes very hard to get the formula for the unknown function. And so we'll get a taste of a few examples where we can find the unknown function relatively easily, but just please be aware that there are people who spend their whole lives trying to solve differential equations, and they barely scratch the surface of it, right? These things are not that easy to do. Okay, so we are going to try to start off by looking at some examples of differential equations. So I'm gonna, actually, let me just start over on the top of this board. Anybody need me to save this any longer? I hope everybody's got it written down so I wish I had a bigger board, that's what I wish. That's what I need a classroom for. But this board will do. I will make it work. The first section in our book is what we're going to start talking about right now, section 1.1. It's called Differential Equations Everywhere. Okay? And in the book, there are lots of examples of places where differential equations come up. I'm not going to be asking you to learn all of those different examples by any means. In this first section, we just want to get just a glimpse, just a brief taste of some places and some examples. So I'm going to give you 3 of them here. The first one is something pretty familiar from calculus or from physics, which I'll call it example A. Position, velocity, acceleration. Okay, so good old classic mechanics here. You have some object and you want to know at any time t, where is that object, right? What is the position of that object? And it's related to its velocity and its acceleration through derivatives. So there's going to be a differential equation there. I'll come back in a minute and fill that in a little more detail. A second application is something called Newton's law of cooling. This one you might not be as familiar with, so I'll go into this in a little more detail. And then thirdly, I'm going to talk about something that's kind of a chemistry application for you, something called mixing problems. Okay? So we only have about a half hour left. I'll see how much of all of these I can get into. I should be able to do quite a bit here. Okay? So let me start with A, which is probably the most familiar one. Okay? And so let's let y of t equal the position of an object at time t. And this is my unknown function. Y of t is the unknown function. I'll write this and I'll get out of your way here. So y of t is what you want to find. Where is this object moving in space at any given time t? All right? But maybe we don't know the position of the object yet, but we do have information about something else. The derivative of that position, which is y prime of t, is sometimes called v of t, and this is the velocity. This is the velocity of the object at time t. So I'm going to use these little ditto symbols to just mean recopy what's right there. That's the velocity, and we also have y double prime of t, the second derivative of the object. This is sometimes written as a of t, and that is the acceleration of the object. Okay? All right. So here we have an unknown function, and we've talked about some of its derivatives. Let's imagine for a minute that the object is simply in free fall, subject only to gravity. So it's just like this marker just dropping to the ground, right? The only force acting on the object is the gravitational attraction to the Earth. Let's just assume that for the purposes of this example. So assume the object is in free fall. It's in free fall. It's just falling down to the ground, right? Under gravitational force. Let's just suppose that the object is just falling under a gravitational force through free fall. What that would mean, guys, is that, assuming it's close to the Earth's surface, you guys probably learned in your physics class or even in calculus that there is an acceleration due to gravity. It's just a constant number that is pulling objects with a particular acceleration towards the surface of the Earth. Okay, so then we have the differential equation y double prime is equal to, it's usually called g, where G is either equal to 9.81 meters per second squared, or if we use the English system of units, 32 feet per second squared. You probably recognize some of those numbers maybe. So this is a first example of a real world example of a differential equation. Y double prime equals 32, or Y double prime equals 9.81, depending on what units you use. Does anybody know how to solve that differential equation? Somebody want to suggest how would you solve this and find the unknown function y of t?
What was that, Professor?
My question is, how do you solve this? We're going to solve a differential equation tonight, which is this one. How do we solve that? If I know what y double prime is equal to 32. How do you solve for y? Ah, Anthony, you're right. You take an antiderivative, or you take, in other words, an integral, and you do it twice, right? So that's exactly right. So to solve, we integrate twice. Okay, so when I do the first antiderivative, when I anti-differentiate a constant, it's really easy, right? So this is just g, which is a number. So the antiderivative would just be gt plus c. The plus c is the constant of integration, right? That you're familiar with probably. And then we do it again. And when we anti-differentiate again, we get 1/2 gt squared plus ct plus another constant, which I'm going to call d. So there is two antiderivatives of the differential equation. That's the unknown function that we're looking for. That tells us the position of this object that is in free fall as a function of time. Actually, it makes sense that it's kind of like a parabola, right? You throw this object into the air, it's going to trace out a parabola shape. Well, that's kind of the formula that you have here. Y of t is a parabolic solution. It's a parabolic curve, I should say. Okay. Now, there's something that I need to point out about this answer in this box. We have our differential equation and we have our solution. This solution, as you can see, is actually many solutions because there are constants here. The numbers c and d can be anything. It doesn't matter what those numbers are, they will still make a valid solution to this differential equation. So this is not just one solution here for the differential equation, it's a whole family of solutions. And so we have a name for this, and I want to give you a little terminology here. This is called the general solution to the differential equation. So this is the general solution to the differential equation. The general solution to a differential equation always has parameters in it. It has constants in it. In this case, the c and the d, right? So anytime you're going to get these questions a lot this semester, find the general solution to the differential equation. If you get asked that kind of question, you should be expecting that your answer will have these constants in it, because every time you write down a general solution to a differential equation, that's what's going to happen. Interestingly, the number of constants that you get in your general solution is actually always the same as the highest number of derivatives in the original differential equation. Makes sense, doesn't it? If this was y triple prime, then we would have integrated 3 times to get the solution, and we would have gotten 3 constants in the general solution. So the number of constants is actually lining up with what I'm going to end up calling the order of the differential equation, the most number of derivatives that is involved in the equation. Now, to find those constants, to find C and D, we would have to be given more information. We would need what are called initial conditions. We would need initial conditions. Those initial conditions would be, so what am I talking about here? When I say initial conditions, this would be like, I would have to tell you what y of 0 is, or maybe y prime of 0. The number of initial conditions that you need depends on how many constants you're trying to find. So in this case, we would just need these two pieces of information. What is y of 0 and what is y prime of 0? Like if I told you that, then you could solve for C and D by just using this equation and plugging in t equals 0 into it, right? And using the value of y of 0. And similarly with the y prime of 0. Okay, so you guys are going to ask me questions, right? If you have any questions. I hope this is all making sense so far. I don't want to go too fast or have anybody kind of lost on the first night. Once you know what C and D are, then among all of these solutions that are part of the general solution, you will have the one solution that matches up with the initial conditions. And that solution is called a particular solution. Okay, so let me actually write down a definition here. A differential equation together with initial conditions is called an initial value problem. An initial value problem. It's a differential equation together with some initial conditions. Initial value problem is often abbreviated IVP. So when you have an initial value problem, you not only have a differential equation that you can solve and come up with a general solution, you can plug in these initial conditions and get a specific solution. It's called a particular solution. So the solution to an initial value problem is called, this is called a particular solution. So you have to keep general solution and particular solution straight. This general solution is the family of solutions where you have constants that are still appearing in the solution. But once I specify initial conditions, if I specify initial conditions, I have an initial value problem, and then I can specifically figure out C and D, and I have what's called a particular solution, which is just one of the solutions among the many that are in this family. Okay, if I'm talking too fast, just let me know. So far, so good? Okay, I was gonna do a word problem with this whole position, velocity, acceleration. I don't think I'm gonna do that tonight. I just wanna leave it at that for now. I can be happy that we actually solved a differential equation tonight. This one was easy. We just had to integrate 2 times from that acceleration formula. All right? Let me take a minute to share with you a couple of other differential equations. And these are equations that we will not be solving tonight because we need to learn how to solve them, which is what's going to happen in the next couple of classes, okay? So the next thing I'm going to do is give you example B, which is about Newton's law of cooling. Okay, this is a nice one because it's not too hard to describe this, but it is hard enough that we don't actually have the tools to solve this differential equation quite yet. All right, so let me talk about this. I'm going to write down what Newton's law of cooling says in words first, and then we'll put an equation with it. Okay, so what it says is, I'm going to put quotes here, the rate of change. That sounds like calculus. The rate of change of an object's temperature, the rate of change of an object's temperature is proportional to the temperature difference between the object and the surrounding medium. Okay, there's a lot of words there. I'm going to make sure you guys have a chance to catch up and write that down. The rate of change of an object's temperature is proportional to the difference between that object's temperature and the temperature of the room. So if I take a cup of coffee and I set it inside of a hot sauna, and let's say the coffee is hot. If I take a hot cup of coffee and I set it in a hot room, there's not much temperature difference between the object and the room. So the rate of change of that object's temperature, the coffee, isn't very much. It doesn't change very quickly. But if I take a hot cup of coffee and I set it out in the freezing cold Alaska or something, right? In the middle of winter, there's a huge difference between the temperature of that coffee now and the temperature of the Alaska winter. So that coffee is going to get colder much faster. The rate of change of that coffee temperature is going to be very fast. At least at first it would be very fast. But then, of course, as that coffee gets colder, the temperature difference doesn't become so much. Eventually, the cup of coffee becomes as cold as the Alaska landscape almost, right? At which point there's a very slow change in the coffee temperature. So it kind of makes sense. This is a reasonable sentence, I think. So there's an equation that we can write with that. Rate of change of the object's temperature, that sounds like the derivative of the temperature with respect to the time. And what does it say? It is proportional to. So there's going to be a proportionality constant. Leave just a little bit of space here right after that equal sign because I'm going to come back and put something next to that equal sign in a minute. The rate of change of the coffee's temperature is proportional to what? To the temperature difference. I'm going to use some parentheses here. The temperature difference between the coffee, I don't know if you can read that very well. That's a T sub M, the temperature of the medium. So the temperature of the object is capital T. The temperature of the medium is T sub M. This is the equation. It's a differential equation for Newton's law of cooling. Okay? So in this equation, K is a constant. T sub M is the medium, the temperature of the medium. And T is the object's temperature. So we have the temperature of the object, the temperature of the medium, the constant, and so on. There's just one little thing about the equation. I said I was going to make a little adjustment. There's one little thing I want to point out. Suppose that you have that hot cup of coffee. So capital T is really big. And you have the Alaska winter medium. So it's very cold. That's a very small number. So if I have a hot cup of coffee in a very cold place, T minus T sub M would be a positive number because the coffee is hotter than the medium. When you subtract them, you would get a positive number here. But then think about the coffee. Is it getting hotter or colder when it's sitting out in the Alaska winter? It's actually getting colder, right? This hot cup of coffee is going to cool down if it's outside. In other words, the temperature is decreasing. That suggests to me that this is a negative number. The rate of change of that coffee's temperature is negative, despite the fact that this part is positive. Well, in order to get a negative number on the left side, while you have a positive number here, the K would have to be negative. So what mathematicians do, because they know that K is going to have to be negative in this formula, is they just go ahead and put the minus sign into the equation from the beginning. So everybody needs to pay attention here and put that minus sign in there. The rate of change of the temperature is negatively proportional to the difference between the temperature of the object and the temperature of the medium. Okay? So that is the equation, and this is not one that we can just solve by integrating right away, like we did on that last example. We can't just integrate this one. It's not that simple. I'm going to show you on Wednesday how we actually solve this equation. But let me do something else for you right now, which is I'm going to draw a graph. My first picture of the semester. I'm going to graph the temperature of the object, the coffee, if you will, as a function of time. Let's imagine that the temperature of the medium is down here somewhere. And I'm going to assume that it's just constant. That's probably not a fair assumption in all situations, but let's just make it easy right now. This is the temperature of the medium. Let's suppose we start off with our hot cup of coffee right here. This is T of 0. Right? The question is, what happens to the temperature of the, I want to draw the graph of what happens to the temperature of this object as time goes on. Right now, it's very hot compared to the medium, which means it's going to cool down. And because this is a pretty big difference, it's going to start off cooling down pretty quickly at first, pretty steeply. But as it cools down, you see that this temperature difference is shrinking. The temperature difference gets smaller, which means that the rate of the cooling, according to the equation, the rate of the cooling gets slower. So this actually starts to flatten out. And in fact, eventually, what it basically does is it asymptotically approaches the temperature of the medium. So this is a picture of the unknown function. So the unknown function, of course, is T of T. This is a picture of it. But until Wednesday, anyway, I don't have an actual equation for you for the solution. On Wednesday, I will show you guys how to solve Newton's law of cooling and a whole bunch of other differential equations. Okay, so this is just a nice example because it's not that complicated. It's a pretty straightforward setup, and it works well kind of on the first night of the semester. Okay, I'm going to give you one more. I promised you 3 applications. I've got about 5 minutes for this. I think I can get it done. Are there any questions about Newton's law of cooling so far?
So does it ever reach the TM or no?
Not ever exactly. This distance will always be positive, but it's going to asymptotically approach it. If you leave that cup of coffee outside on that cold Alaska winter landscape, the coffee will always be a little bit warmer than the temperature of the winter in Alaska, but it's going to get asymptotically close to it.
Okay, thank you.
Yeah, it's fascinating how that works. Okay, so we're going to come back to this on Wednesday. It's a little bit of a cliffhanger to get you to come back to see that, but I want to do one more example tonight, and then we'll call it a night. This way, you guys will be able to start the homework even after tonight's class. And you know, I haven't gotten everything all explained yet, but it won't be that bad. You'll be able to get it started. Let me talk about what I call mixing problems. This is a chemistry example. I'm going to draw a picture of the setup of this. Let's imagine that I have a beaker here that's filled with a chemical that is dissolved in the beaker. And A of t, this is actually the unknown function. What is this? A of t that is inside of this, flask here is the amount of chemical at time t. So maybe you've got some salt that's dissolved in here, right? And you just have some amount of grams of salt. I'll just imagine that we're using the units of grams for this. Whenever you're doing chemistry problems, you always have to keep your units clear. Okay? So if this was the picture and this was all that was happening, well, the chemical, whatever however much salt is in there, would just be constant. But I want to imagine that we are pouring, we have some kind of a hose or a faucet here, and we are pouring chemical into this tank. I'm going to label a couple of letters here that I will explain in a moment. I'm going to write R1 and C1 next to that inflow of chemical. So maybe there's some salt being poured into this flask, right? Which would be affecting A of t. And at the same time, I want to imagine also, let's edit our picture a little bit more. I want to imagine that there's a little bit of a leak in the bottom of this flask. And I'm going to write the letters R2 and C2 underneath there. All right, so you might be losing some salt out of the bottom while you're gaining some salt that's being poured into the top. All of that affects A of t. Now, what are the R1 and the C1 and the R2 and the C2? So R1 is the flow rate into the tank. I'll call it a tank, I guess. A flask or a beaker or a tank, I don't really care. It's the flow rate. So this would be in units of like liters per minute. Let's just imagine it's something like that, liters per minute. And R2 is going to be the flow rate out of the tank. So it's just sort of how strong the liquid is pouring in and out of the tank in units of liters per minute, okay? And then C1 is going to be the chemical concentration into the tank. We have to know like how much salt is going into the tank. Maybe this is just water pouring in, right? Or maybe it's got a lot of salt in it. That's going to make a difference. This is going to be in units of grams per liter, right? And then as you can imagine, C2 is the chemical concentration out of the tank in the same units, yeah? Okay, so I'm almost out of time. Just give me like a couple more minutes to finish this up. It'll be really nice so that I don't have to like cut off right in the center of this little discussion. So I'll try to make this really fast. I'm going to write down a differential equation now for the amount of salt or amount of chemical at any time t. And here it is. dA dt. This is the rate of change of the amount of the chemical at any time t, right? Let me first just write it in words. It's going to be the rate of chemical in minus the rate of chemical out. Okay, so you just subtract. Like, at what rate is the salt pouring in from the top, and at what rate is the salt going out from the bottom? Just subtract them, and that's your net rate of change of the amount of the chemical here. Now, when I say rate of chemical in, I mean in like grams per minute. This is a grams per minute minus the rate of chemical out is also measured in grams per minute. See? dA dt, what are the units? Grams per minute, right? So, real quick, this is just a subtraction. The rate at which the chemical goes in, do you see how to get grams per minute out of your units here? You just multiply the R value with the C value. It's just simply, I'm going to write it here, R1 C1 minus R2 C2. That's it. Okay. And let me do one last thing. I know I'm pressing my time here, but you'll be happy to have this done so you don't have to worry about figuring this all out again on Wednesday. Here we have the equation. I'm going to rewrite it. I'm going to add the R2C2 to the left side. Like that. So the ADT plus R2C2 equals R1C1. And then the last thing I'm going to simply say is that we can replace C2 as follows. So the ADT, this is a differential equation that we are not going to solve tonight, but that we will know how to solve by the end of the week. Okay? Plus R2 times, now C2. I want to say something about C2. That's the concentration of the chemical that's coming out of the tank. If you think about concentration from a chemistry perspective, it's just sort of the amount per volume of this chemical. It's simply the amount of the chemical, which we already know what that notation is. It's A for the amount, divided by the volume of the tank. Right? The volume, how much liquid is in this beaker, okay? And that is supposed to equal R1 times C1. So here it is. This is the differential equation for mixing problems. We're going to come back to this later. I have to explain how you find the volume, and then how to solve the differential equation as well. So there's more to this than just what I've done tonight. But I at least just wanted to get this up here. Are you guys able to hear me okay? It's really quiet in the background where I am.
Your mic's a little staticky.
Yeah, your
Sometimes.
mic's making a lot of noise.
It's my mic that's doing that?
Yeah.
Sometimes.
Okay, I don't know. I'll have to look into that. I haven't had a problem with that before, but interesting.
I just started right now though.
Oh,
For me.
Yeah, it started about 5 minutes ago. It just started sounding really staticky.
Yeah, about around there.
shoot. Okay. Yeah, nothing really changed on my end, so I can't really explain what might have happened, but
It just stopped, actually.
Oh, yeah. I
Just
can't hear
meant
it
that
now.
the internet slowed down for a minute at my house. This is what I said. Something like this could happen, and we suddenly have to stop our class or whatever. But thanks for letting me know, and do let me know if things like that are happening again, and I'll see what I can do. Okay. This is all I've got for you guys for tonight. Thank you very much for coming. Sorry to keep you a couple extra minutes, but I wanted to get through this. I will look forward to seeing you right back here on Wednesday for our class. And feel free to start working on the homework and sending me questions if you have any. I'll be glad to do everything I can to help, or if you need help getting access to some of the book, anything like that, just let me know. For now, I'm going to let you go, and thank you guys very much. I'm glad to see you, and we'll talk again soon.
All right. Good night, Professor.
Good night, Professor. Thank you.
Good night.
Safe out there.
Sir.